Good evening, everyone. Please, am I audible?
Yeah, you're edible.
All right, thank you.
Can you please increase your voice a little bit?
All right, please. All right, please. That's very well noted. That's very well noted. That's very well noted. So, we can start today's section, I believe. We can start today's section. So today, we are currently a little bit behind, okay? We have about 3 topics to catch up when it comes to DCIT 203. So today I would want us to continue from where we read the last time. We did look at logic gates, Boolean algebra. We looked at QUINE Maps. So today let's look at the QUINE McCLUSKEY minimization method and then finish it. So we'll open it today and then we will finish it today. Pick an give out an example that we work on our own. I believe we'll be fine. So please, if we are all together, then we can begin. Okay, then we can begin. All right, so let us start. So we looked at K-maps, or we looked at minimization. So when we talk about the QUINE McCLUSKEY method, we are still within the subject of minimization. Okay, so we looked at minimization using Boolean algebra, right? Where we spoke about the Boolean laws, we talked about commutative, distributive, associative, we talked about the identity law, we talked about De Morgan's law, we talked about all those things, okay? So aside that, we also looked at how to minimize using K-maps. Okay, so we said that if you are given a scenario, okay, or you are given a simple Boolean expression, or a simple logic expression of the kind, let's see, AB plus AB prime, okay? If you have something like this, you don't have any business with, let's say, QUINE McCLUSKEY minimization method, or maybe even K-maps. Ideally, this, you can use Boolean algebra to work this out quickly within minutes, and then you are okay. On the other hand, if you are to have, let's say, something like ABC plus, let's say, BC prime or prime. If you have this, you can decide to use K-maps, or you can decide to use Boolean algebra. This has 3 variables, right? So the first problem here has 2 variables, and the 2 variables are A and B, right? The second problem has 3 variables, which is A, B, and C. Now you can have other problems with like 4 variables, like let's say A, B, C, D. Let's say this is prime, plus A, B, C prime, D, plus A prime, let's take B prime, C prime, D prime. Now, if you want to work out this problem using Boolean algebra, you will encounter a problem. And the problem you will encounter is that, look, this is going to be very, very, very tedious to work out, okay? It's going to be a lot tedious and complicated to decipher your way around, or to find your way around. And it might not be very, very convenient. So why don't you use K-maps to solve this? If you have 4 variables, you are okay using K-maps. Okay, so you have 4 variables, A, B, C, and D. Okay. So we said when we are looking at the variables, we don't care about what is primed or what is not primed, or which alphabet has a bar or which does not have a bar. We are talking about the number of unique alphabets or the number of unique characters in that particular expression. So we stated that all these are some of product expressions, right? So we want to look at the unique characters in all this. Those gives us the set of all possible variables. And this, we know that this is a 4-variable expression. So with a 4-variable expression, the ideal method that we can use is our K-maps. Okay, it is not necessary to use, let's say, the QUINE McCLUSKEY minimization method for a 4-variable operation. The K-map is much simpler and easier to use when dealing with this kind of problems. But assuming you have a problem which contains a fee variable, let's say E, okay, would you want to use a K-map? So for 5 variables here, using Boolean algebra is out, because how are you going to apply the laws to this to solve them? It becomes extra tedious. And look, you end up applying more efforts to solve a problem as you could have been able easier if you would have used other methods, okay? So with something like this, we are looking at using, let's say, the K-map, okay? We can use a K-map to work this out. Or otherwise, if we do not use a K-map, the most ideal method will be a QUINE McCLUSKEY minimization method. So if our variables are 5, if they are 6 or more, the most ideal method is a QUINE McCLUSKEY method. If the variables are, let's say, 3, 4, or sometimes 5, okay, we can consider our K-map as our most ideal method. But if our variables are 2 or 3, then we want to consider Boolean algebra as our most ideal method to solve those kind of problems or to work out those kind of problems, okay? So moving forward, we've already looked at how to apply Boolean algebra. We looked at how to apply K-maps. So now we have to look at how to apply the QUINE McCLUSKEY minimization method to solve problems or to minimize expression. Yes, please.
Please, I want to ask a question.
All right.
Please, can you choose to use the QUINE McCLUSKEY to solve any expression at all?
Can you use solve what?
Any expression at all, whether it is 2 variables, 3 variables.
Oh yeah, it would work. It would work. But you see, you want to look at the time, you want to look at the efforts, and you want to look at how tedious it will be to use. Okay, we all know how the QUINE McCLUSKEY method is. Okay, that is if you are familiar. It has series of steps and processes that has to be followed. Okay, and now imagine repeating all those processes whilst we could have just apply some of them straightforward. You can just look at it and be able to know that, okay, this is we know this is 3 variables, right? And everything is much clearer if you have to apply a Boolean laws. In, let's say, 2 or 3 minutes, we should be able to have our minimized version. But if for that same problem, we decide to ignore our Boolean laws, okay, and rather decide to venture, let's say, K-maps or QUINE McCLUSKEY, you might end up stressing ourselves, okay? So though sometimes, like maybe a 4-variable K-maps, there are a whole lot of alternatives, but I want to use a method that will save you time and save you effort at the end of the day. Okay, so that is the whole idea, is to use a method that is most convenient, that would save you time. All right. So sure. So when it comes to the QUINE McCLUSKEY method, it's another name for it is a tabular method or tabulation method, and usually it is much how do you call it, systemized, or it is much more, how do I even put it, like it's much more of a programmed method. Okay, it isn't something that is ideally manually calculated or manually employed. So we assume that sometimes you can have expressions with as much as 6 or 7 variables, okay? And I'll try, and then we take a question of that sort today. We look at expressions having more number of variables, having more number of variables, and then we see how we would be able to use how do you call it, our QUINE McCLUSKEY method to solve those as well. Okay, so now let us look at a 4 variable expression. Okay, we know that with our 4 variable expression, we can also use our QUINE McCLUSKEY method, but ideally a K-map is good to solve that. But when understanding the QUINE McCLUSKEY method, using a 4 variable expression is much ideal because it's much easier to work around and looks less tedious or complicated. So let's take an example. Okay, so with this example, we are going to look at the most important things that you need to be able to understand when working around our QUINE McCLUSKEY method is our prime implicant. Okay, let me put it as PI. Okay, then we have our essential prime implicant. Okay, so now what does this tool means? Let's try and then understand this together. Okay, so when we talk about our implicants, we are only talking about group of ones. Okay, so whenever we are talking about grouping our ones, they are implicants. Okay, so we've looked at this under K-maps, right? We've looked at this under K-maps. So we said that after you've arranged your minterms, what you do is that wherever a minterm is represented, you put 1 there, right? Exactly. So in any box or in any square where a minterm is given, you put 1 there. And after that, you group adjacent ones. We said you can group in the powers of 2, right? So we said 2 is the power 0, 2 is the power 1, 2 is the power 2, etc. So it can be, we can group 1 ones, we can group 2 ones, we can group 4 ones, we can group 8 ones, etc., etc. Okay, so the whole process of grouping these ones, or when we group these ones, what we obtain is what we call implicants. Okay, but sometimes under K-map, you realize something here. You realize something here that there might be a scenario, a case where our ones are repeated. Let me just draw something simple. And let's use this as our example or illustration. So we have, let's say 1, 1. Let's say we have 1 here. We have 1, 1, 1. Okay, and let's say let's just ignore the rest. So this is the example that I want to illustrate here for you. Okay, so this is the thing. You can decide to, following this rule, we said you can select 1 single one, right? And technically, you are correct. You can decide to select 2 ones. Technically, you are correct. All these are implicants. But when we are talking about prime implicants, we are talking about the largest group of ones possible or selectable. Okay. And when we are talking about the largest group of ones, we are talking about adjacent ones. We don't want ones that are occurring in this manner, as in this. No. This is not allowed. We are talking about adjacent group of ones. So here you can see that the largest group of ones is 4, right? So that largest group of ones is called our prime implicant or our PI. Okay, it's called our prime implicant or our PI. Now, after labeling all your prime implicants, okay, there are some scenarios where you realize that there is a particular prime implicant. At the end of the day, after you've selected all your largest group of ones, okay, you realize that there are some specific prime implicants that are covered by other prime implicants. They have no independent members. Okay, how do I even illustrate that? Let me draw a new K-map for us and use that to illustrate that. Right, so let me draw a very simple K map. This would be okay. All right. So we have a 4x4 cell K map or a 16 cell K map. Okay. So let's have this scenario. We have our 1 here. We have our 1 here. Okay. When we are grouping, you know that we are going to group. Let me use red to do the grouping. You know we are going to group this, right? We have 1 here. We have, let's say, 1 here. We have 1 here. We have 1 here. You know we are going to also group this, right? This is 4 group of 1s. So we group it. Now let's say here we have another 1 here, we have 1 here, we have 1 here. This another 4 group of 1s. Let's group it. Okay. Now with this simple thing that we've done, how many prime implicants do we have? We have 1, we have 2, we have 3, right? We have 3 prime implicants here. Okay, that is the largest group of 1s. But now we want to ask ourselves that how many of these implicants are essential? And for us to denote our essential prime implicants, we want to inspect our prime implicants and ask ourselves that how many prime implicants have at least one unique member? Okay, I just want to use this term so that we understand. One unique member, that is a member which is not covered by any other prime implicants. So if you look at this particular box here, okay, we can see that we have 3 different different implicants that have not been covered or that is not covered by any other prime implicant. Okay, but if you look at this particular here, what do we see? We can see that this square here has been covered by this. This square here has also been covered by this selection here. So at the end of the day, all members here have one way or the other been covered by other prime implicants. So we can say that this particular one here, although it's considered a prime implicant, but it is not essential. Okay, it is not essential. At the end of the day, if we decide to include that in our final expression, it's going to create a redundant value. Okay, it basically complicates our expression and adds no reasonable it just complicates our entire expression. Okay, it makes everything tedious. So we just eliminate that and stick with R prime implicants. Okay, so that's what we mean by prime implicants and implicants. So essential prime implicants are prime implicants, all right, but we have to have at least one member that is not covered by any other prime implicant. Okay, so if that happens, we call or we say that prime implicant is essential. All right, so now that we understand what our prime implicants and essential prime implicants are, let's take a question and then use our question to illustrate the method. Okay, so we have F into bracket A, B, C, D. Okay, and the mean terms are I'm coming. So the mean terms are 0, 2, 4, we have 6, we have 8, we have 9, we have 11, we have 13. Let's add 15. Okay. So now, let me clarify this. So if you want to know which kind of, how many variables this expression originally holds, you can just look at this
Hello,
place.
please. The line is breaking.
Okay. Please, is it still breaking or it's better now?
Oh, it's okay.
It's okay.
All right, then let's progress. So we have this particular.
Mr. Isaac,
Yes, please.
your line is breaking. I hardly hear you.
No,
Yeah.
you see that your line is breaking.
It's from your end, bro.
Mr. Nyako, please check your network.
Oh, please, will you try signing out and signing in again? Probably that call fixed things up for you. Okay, sir. So can we progress? So we have this right here. So first of all, we want to know how many variables are we dealing with here? The question states explicitly that this is a 4-variable expression, or this expression has 4 variables, right? And you can see that from this place, right? The function is defined as having 4 variables A, or having the variables A, B, C, and D. Please, can you all see that here? Right? And then the corresponding mean terms for that expression is, then we are giving as 0, 1, 2, 4, 6, whatsoever. So now you know that if we were K-map, we just draw our K-map. We know this would have been a 4x4 K-map, right? We said that to determine the number of squares in that K-map, we use 2 raised to the power n, right? Where n is your number of variables. So for us to have known how many squares this K-map will occupy, we used 2 raised to the power. The number of variables are what? 1, 2, 3, 4. So 2 raised to the power 4. We know that we would have been using a 16-cell K-map, right? And a 16-cell K-map can be represented as a 4x4 K-map. That will correctly cover this particular mean terms or this particular expression. So if we were to be using a K-map, we could have ideally used a 4x4 K-map. Or in the scenario where the question does not correctly or does not explicitly give you the number of variables contained in the expression, there is still a way you can be able to know. Just look at your given mean terms and ask yourself, what is the highest square that was denoted? It's 15. And if the highest square is 15, you know straight away that's a 4x4 K-map. Because you know that when labeling your 4x4 K-map, the highest square you can record is cell 15, or the highest cell you can record is cell 15. So straight away you'll be able to know that this is a 16-cell K-map. Okay. And that will accurately cover all these mean terms. Otherwise, when you are giving, let's say, how do we call it? Let's say the last mean term that has been represented there is 7, or that has been given is 7. You know certainly that is a 2x4 K-map, or that's an A-cell K-map. So you can just use that to be able to find your way around things, just in case the question does not explicitly state the number of variables in there. Okay. But as this one does, we can go straight away and then work this out. So how do we do that? Step 1, or the first step, is that we want to know the binary equivalence, okay, of our given mean terms. So what is our given mean terms? We have M0, right? We have M1. So we have M0, right? We have M1, we have 2, we have 4, right? We have 6, we have 8, we have 9, we have 11.
Hey, I hope that may how yeah. Oh, okay.
Oh, Mr. Nyako, please. Mr. Nyako.
13, 15.
Hey,
Mr. Nyako.
more bread.
Mr. Nyako.
Please, your microphone has been unmuted, and we're actually listening to the conversation.
Please, you can continue, Mr. QUINE.
Okay. So these are giving mean terms, right? We have M0, we have M1, we have M2, M4, M6, M8, we have M9, we have M11, we have M13, and we have M15. Okay. So the first thing that we are going to do is that we are going to first denote the binary equivalence of this, of each of our mean terms. So 0, we are going to convert 0 to binary, but then we want to keep the number of bits to our variables. So how many variables do we have? We have 4 variables, right? So if we convert this, we are going to convert 0 into 4 bits, okay? So if you convert 0, you know that the automatic binary equivalence of 0 is 0, right? So automatically we are going to add or put 3 zeros in front of it, okay? And we now have our 4 bits. And now what are variables? Our variables are A, B. Please let me do things much more proper so that moving forward, we don't struggle, okay? So let me draw this right here. So we know our variables, we have our A, okay? And then we have B. We have C. And then we have D, okay? So we can label this side as our mean terms. Okay, so our mean terms, and let me just put that here. So we have 0 here, right? Okay, good. So we have mean terms and they are binary equivalents. And this is the first thing that you always have to do. Okay, so we know 0 is 0, right? But we need 4 bits. So all the remaining cells, we fill them with 0. Okay, 1. We know 1, the binary equivalence of 1 is 1, right? So 1, we put our 1 here and we do what? We fill everything else with 0, 0, 0 because we need a 4-bit representation. So when we take 2, we know 2 is 1, 0, right? So we fill everything else with zeros so that we get our 4-bit representation. When we take 4, we know 4 is 1, 0, 0, right? And please, you all remember how we can get 4, right? I think with 4, we have 2 raised to the power 2, right? So 2 raised to the power 2 is present, so we label it as 1. 2 raised to the power 1 is absent, so we label it as 0. 2 raised to the power 0 is also absent, so we also label that as 0, right? So automatically we know 4 is 1, 0, 0. Okay, so we put our 0 in front. Now when it comes to 6, please, you can just use a calculator for all this, okay? So when it comes to 6, I think 6, you have 2 raised to the power 2 plus 2 raised to the power 1, right? 2 raised to the power 2, you have 1. 2 raised to the power 1, yeah, you have 1. 2 raised to the power 0, you have 0, right? I believe you are right.
0, 1,
Yeah,
1,
so
0.
we have 1, 2, 3. Yeah, so we have 1, 1, 0. Then we put our 0 in front. So please, 6, what are we getting? No. What did this is
Please,
for,
that one's for 6.
No, this is for 6, right? Please
Yeah,
let me
yes, sir. Yeah.
denote that properly. Okay, so that moving forward, we are not found wanting. So this is 6 that we just did. Then 8, what are we getting? I think 2 raised to the power 3. So we have 1, 2 raised to the power 2, we have 0, 2 raised to the power 1, we have 0, 3 raised to the power 0, we have 0. Are you right? So we have 1, 0, 0, 0. So now we have 2 raised to the power 3 plus we have 2 raised to the power 0, right? So this gives us 1, 2 raised to the power 2 is 0, 2 raised to the power 1 is 0, 2 raised to the power 0 is 1. So we have 9 to be 1, 0, 0, 1. So 11, what are we getting? Please, 11, what are we getting? So 11, we have 2 raised to the power 3 plus 2 raised to the power 1 plus 2 raised to the power 0, right? 2 raised to the power 3 is 8 plus 2 raised to the power 2 is 2 raised to the power 1 is 2. That gives us 10. Plus 2 raised to the power 0 is 1. That gives us 11. Okay, so this is 1. 2 raised to the power 2 is 0. 2 raised to the power 1 is 1. 2 raised to the power 0 is 1. All right, so sorry. So this gives us 1011.
Let me try it.
Yes, sir.
Is it 1101 or 1011?
2 raised to the power 3 is 1. 2 raised to the power 2 is 0.
It's 1.
Right.
Is it,
No, 2 raised to the power 2 is absent too. So that's
okay.
0. Then we have 13. 13 gives us 2 raised to the power 3 is still 8, right? We have 5 left. 5 is 2 raised to the power 2, then 2 raised to the power 0, right? So 2 raised to the 8 plus 4, that's 12 plus that's 13. Please, you in examination or something, you have calculated, so you don't need to be doing this. Okay, so myself, I don't have a calculator here, that's why. Okay, so 2 raised to the power 3 is present, 2 raised to the power 2 is present, 2 raised to the power 1 is absent, 2 raised to the power 0 is absent, right? It's present, I mean. So 13, we have 1, 1, 0, 1. Then 15, what do we have? We have 2 raised to the power 3, right? 8. We have 7 left. We have 2 raised to the power 2. We have 3 left, right? 3, you have 2 raised to the power 1, and then 2 raised to the power 0. So 2 raised to the power 3 is present, 2 raised to the power 2 is present, 2 raised to the power 1 is present, 2 raised to the power 0 is present. So we have 1, 1, 1, 1. Please, if anyone has a calculator, kindly get it close, okay, so that in case we need anything, you just put it for us. Okay? All right, so please, now we've all gotten the binary equivalence of our minterms, okay, which is the first important step. So after we've gotten this, we can now come and start grouping, okay? So when we are grouping, we will now label our group. So this is our group. Then we have our pair, okay? So let's take our pair, and then we have our A, B, C, D. All right, so let's have this right here. Okay. Here's my hometown people saying that. All right, so all right. Let's see. Um, All right, so I think this would work. So now we want to now group our binary equivalents for our midterms, okay? And when we are grouping, we group them according to the number of ones, okay? So please, let's take it again. We want to now group this. We've seen that 0 is 0, 0, 0, 0. 1 is 0, 0, 0, 1. 2 is 0, 0, 1, 0. 4 is 0, 1, 0, 0. 6 is 0, 1, 1, 0. 8 is 1, 0, 0, 0. 9 is 1, 0, 0. 9 is 1, 0, 0, 1, right? 11 is 1, 0, 1, 1. 13 is 1, 1, 0, 1. 15 is 1, 1, 1, 0. Okay? So now we want to compare or group them according to the number of ones which are there. So we are saying that any mean term, okay, that has, let's say, the ones with 0 ones, no ones, we'll put them in one group. The ones that have only 1 ones present, we'll put them in one group. The ones that has 2 ones, we'll put them in one group. The ones that has 3 ones, we'll put them in one group. The ones that has 4 ones, we'll put them in one group. Okay, so that is what we want to do. So we'll first come and inspect and ask ourselves, how many ones does 0 have? 0 has no ones in them. So that will automatically be our first group, right? That will automatically be our first group. So we call that our group 0. Okay, and our 0, which, oh no, guys, forgive me, please, which mean 10? So group mean 10, okay, that's for me. So we have our group, which is group 0, right? So group 0, how many, which mean term are we bringing there? That is 0, right? And we said 0 has how many zeros? It has 4 zeros, no ones in it. So we put it at group 0. And let's ask ourselves, is there any other, let's inspect, is there any other mean term that has no ones in it again apart from 0? Please, no, there is no other mean term there that has no ones. If you look at 1 has 1 ones, right? If you look at 2 also has 1 ones. If we look at 4 has 1 ones. If you look at 6 has 2. 8 has 1. 9 has 2. 11 has 3. 13 has 3. And 15 has 4, right? So apart from 0, no other mean term has no ones in them. So we can classify this as belonging to one group, okay? So we ascribe this to its own group, which is group 0. Now let's take group 1. Group 1, we are going to take mean terms that have only 1 ones in them. So we'll come and inspect again, and then identify all mean terms that has only 1 ones in its binary equivalent. So let's inspect. We know 0 is already covered in group 0, right? So there is no need coming back to it. This is already covered. So we now come to ones. Ones has how many ones? It has only 1 ones, right? So we know we can bring it here as 1, right? And what is the corresponding binary value? 0, 0, 0, what? 1. And then now let's look at 2. And then let's ask ourselves, how many? Yes.
Please, can you take that part again?
Okay. So we want to group with regards to the number of ones that are contained or that are present in the binary equivalence of our mean term, right? So we said that in TSA, okay, please, everyone understands free, right? In TSA, offer 0, okay. Say you inspect the binary equivalence of 0, it does not have any ones in it. Into you know you the better one group. By a mean term 1 or mean term 1, and we inspect the A, B, C, D, which is a binary equivalence of 1, you will see that it has only 1 in it. So that one will also belong to another group, which is the group with only 1 minterms. Then we come and inspect 2. You will see that 2 is also 0, 0, 1, 0. So how many ones does 2 have?
1.
1. So that one will also be in the same group as 1. Then we come and take 4. How many ones does 4 also have? Let's look at this carefully. 4 is 0, 1, 0, 0. How many ones is there?
Only 1.
1. So do we put it in the same group or we create a new group for it?
We put it inside the same.
We put it in the same group because it also has only 1, 0. But when we take 6, 6 has 2 ones. So do we put it in the same group or we create a new group for it?
We create a new group for it.
We create a new group. Now we come and take 8. 8 has only 1, 0. So do we put it in an already existing group or we create a new group for it?
The already existing group.
Exactly. That is a group with only 1 ones. Then we come and take 9. 9 also has 2 ones. So you see that we already has a group. We've already created a group that has 2 ones, right? So we will put 9 there. We take 11. 11 has 3 ones. Now we don't have any group that has 3 ones. Okay, so we create a new group for that and put it there. We come and take 13. 13 has 4 ones. So we know we don't have any group that has 4 ones. So we create a new group, we put it there. So I don't know if you are getting me now. So we just want to make sure that we grouped all of them according to the number of ones that they contain. So if you look at any group, the number of ones in all groups should be the same. So if a specific group has members that contains 2 ones, all the members of that group should only contain 2 ones. We don't want to see any member with 3 ones in it. If we take or we look at a group that contains 4 ones, we don't want to put in there any group that contains anything else than those number of ones. I don't know if you are good with that. So now we have 1, right? We said 1 contains only 1 ones. Which one also contains 1 ones? That is 2. 2 is 0, 0, 1, 0. It contains only 1 in it. So we can put it in the same group, which is group 1. We don't need to say create a new group for that. So we have 2. 2 belongs to the same group because it has only 1 number of 1 in there, which is 0, 0, 1, 0. Okay. Apart from that 1 single 1 in there, everything else is zeros. So now we come and then take 4. 4 is 0, 1, 0, 0. It also has only 1 in there. So we don't have to create a new group. We have to put it in the group belonging to 1 ones. Okay. So that is 0, 1, 0, 0. Now, when we come and look at 6, we realize that 6 has 2 ones in it. But then the group that we have here has only 1 1, not 2 ones. Okay, we don't have any group created that has 2 ones. So that means we have to create a new group. And let's call this group 2. So group 2 is a fresh group altogether. And that will contain members with only 2 ones in them. Okay, so we know 6 has 2 ones. So we'll put 6 in this group. So we take 6. 6 has 0, 1, 1, 0. And then we come to take 8, right? 8 has how many ones? 1 ones. Okay, so we can see that 8 has only 1 ones in there. So do we create a new group for it, or we can put it in an already existing group?
An already existing group.
Good. And which group is that?
Group 1.
Group 1. Because group 1 has members with only 1 zeros, right? So we can put that here. So we have what? We have 1, 0, 0, 0. Very good. So now we've already covered. Ideally, once you are done with any way, in order not to confuse yourself, just take it. Okay. If you take it, you know you've already apportioned a group for it. So you don't mistakenly come back to it again and then create a repeated way, which will mess up your whole work. Okay. So we now come to 9. So when we come to 9, we know 9 is 1001. How many ones is in there?
2 ones.
2 ones. So do we create a new group or we put it in an already existing group?
An already existing group.
That's which group?
Group 2.
2. So because group 2 has members with 2 ones, right? So we have 1, 0, 0, 1. Okay, so now we are done with our 9 here. So now we come to our 11. 11 is 1011. How many ones are contained in there?
3.
3 ones.
3.
So can we assign it to any existing group or we have to create a new group?
You have to create a new group.
We have to create a new group because you don't have any existing group that has members with 3 ones. So if we try to add it to any already existing group, it will not work out, or we wouldn't be able to find any group to include that in. So when it comes to group 3, we are talking about members with 3 ones, right? So 11 has 3 ones in it, which is 1, we have what again? 0, 1, 1, which is 3 ones. Now we have our last member, which is 13. How many ones does 13 contain?
3 ones.
13 contain
3 ones.
3 ones. Oh no, 13 shouldn't be our last member, right? I think we are 15. Okay,
Yeah,
so 13 is not our last member. Yeah. So 13, how many ones does it have? It has 3 ones, right? So can we assign it to an already existing group or we have to create a new group?
Already existing group.
Already existing group, which is group 3, right?
Correct, yes.
Because group 3 already contains members with 3 ones. So we just put 13 there. So we have 1, we have 1, we have 0, we have 1. So we found a group for 13. Now let's look at 15. How many ones does 15 have? 15 is 1, 1, 1, 1. How many ones is there?
4 ones.
4 ones. So do you already have a group for it or we create a new group?
You create a new group.
You create a new group because you don't have any group that is already housing members with 4 ones, right?
Exactly.
So we need a new group. Let's call this group 4. And you're already done with 13, right? So group 4, we have 14 here, and it contains members with 4 ones, which is 1. No, 15. Not 14. So we have 1, 1, 1, 1. Are we together? So now we know 15 has been covered. So we can now see that every member has been ticked. So we know that we are done with this table. This first table, we are done. And we are not coming back to it again. Okay. So we are done with this table. Now we have to work with this table, or we now have to work on this table. So please, did you all understand how we obtain this particular table here?
Yes, sir.
Okay. So if we all understand, then we can progress, right? So we'll open another table again. Okay. So and this table, the labeling is going to be almost the same. Okay. So we have our group number, and then instead of minterms, now the next method or the next step is that we are going to group our minterms. Okay, and we call that our grouped pair. Okay, or let's say our pairs. Okay. So to make this, you can write it as grouped pairs. Or to make this simpler, let's just write it as pairs, okay? And then we have our A, B, C, D again. All right, so we have our A, B, C, D again, okay? So let me draw my line. That is okay. And then we have this, okay. So now we have our group, we have our pairs. So our pairs is just we grouping our mean terms. And please, there is a general rule that governs how our mean terms can be grouped, or which mean terms we are going to group, and we are going to look at that, okay. So now let us look at how we are going to group our mean terms. So here we are going to inspect our mean terms, okay. Initially, we said that we were looking at grouping them according to the number of ones that we have. But in this case, we are grouping them according to the mean terms that differ by only one bit.
Yeah.
Yes, please. Yes, sir.
Yeah, Rebecca. Can you hear me?
Yes, please. Yes. Yes, sir, we can hear you.
So we can continue.
All right, so let's progress. Let's progress. So here we want to compare, okay, according to our mean terms that differ by at least one bit. That differ by just one bit, not at least, please. That differ by just one bit. Okay. So we are comparing. Please, you cannot compare two members of the same group. Okay. So you cannot compare, let's say 1 and 2, 1 and 4, 1 and 8. It's not allowed. Okay. You are comparing members of one group to members of another group. Okay. So we can compare this thing. We can compare 0, mean term 0 to 1. You can compare 0 to 2, 0 to 4, 0 to 8 is allowed. Okay. Or that's the correct way to do it. Then after that, we take 0. That is, we've done doing a comparison for 0. Then we come and take 1. Please, you cannot compare 1 with 2, 1 with 4, and 1 with 8. No. The rule states that you compare one group with the succeeding group, which is the next group. Okay. So you can compare this group to this group to this group, this group to this group, and then this group to this group. Please, I don't know if you are okay with that. So we compare group 0 to group 1, group 1 to group 2, group 2 to group 3, and then group 3 to group 4. It is a little bit tedious, but if you do it right, you obtain the correct result. So let us do that. All right, so let us do that. Are we all together?
We are together, sir.
Yeah, okay. All right. So we progress from here. Let's progress from here. So I said we are comparing, okay, and we want to look at identify the mean terms that differ by only one bit, okay, obeying the laws of our merging. Okay, please. I mean, this place you can also call it merged pair. Okay, most of you might be familiar with that, and you can call it merged pair because all the pairs there are actually merged. Okay, so now let's compare 0 to 1. We said that is the first comparison, right? So if you compare 0 to 1, let's ask ourselves the question: does 0 and 1 differ by only 1 bit? How do you know 0 and 1 differ by only 1 bit? Let's do a direct comparison. Compare the A to A, okay? B to B, C to C, and then D to D. That's how you compare. Please, I believe we are together. So if you compare A in midterm 0 to A in midterm 1, realize that they are all 0, 0. They are the same. If you compare 0 in midterm 0 to 0 in midterm 1, we can see they are all 0, 0. They are the same. If you compare 0 in midterm 0 to 0 in midterm 1, we know they are 0, 0, so they are the same. But then if you compare the D, which is 0 in midterm 0, our midterm 1 rather has 1. So we can see that that one is changing. So we can see that only one member changes. That is what we want, or that is what the law says to identify. Only one member should change. Everything else should be equal or should be the same. Okay, so assuming this place was 1 and another place had also changed to 1, we cannot record that, or we cannot merge those pairs. We can only merge pairs which are only changing in 1 bit, just 1 bit. It doesn't matter where the change is occurring, whether A, B, C, or D. Okay, so far as it's only changing in 1 bit, and all other bits are held constant and are not changed, or are not changing, then we can merge them. Okay, so we will now create our first group. Let's call this group 0. Okay, so group 0, we can see that our midterm 0 and our midterm 1 satisfies our condition. That is, only 1 bit is changing, which is bit D. Okay, so we now we can merge 0 and 1. Okay, so we say 0, 1. These two have been merged. Okay, so we are merging them because it is only 1 bit that differs in the two midterms. And what is our A value? Our A value for both is 0. Our B value for both is 0. Our C value for both is 0. But our D is changing. So we can either write 0 or 1. So we just put a dash. Please, are you seeing it? So if we get to the particular field where the change occurred, we put a dash there. Are we together? Please, did you all understand what we just did?
Yes, please.
All right. So we come and then compare our 0 again to 2. Okay. So we'll compare 0 to midterm 1, 0 to midterm 2, 0 to midterm 4, and 0 to midterm 8. But we cannot exceed midterm 8 because we can compare group 0 to group 1. And apart from 8, everything else is outside group 1. So we cannot compare with 0, which is in group 0. Okay. So if we compare midterm 0 to midterm 2, let's see if it only differs by 1 bit. A is constant, which is 0, 0, right? B is constant, we have 0, 0. C is constant, we have 0, 0. D is also no, C is changing. C is changing. We have 0, 1, right? So we've now identified 1 bit that is changing, but D is held constant, which is 0, 0, and this satisfies the rule. Only 1 bit is changing, which is at C, right? So we can now come and merge 0 and 2 as well, right? Because it satisfies our rules to merge. Okay, so A is held constant, which is 0. B is also held constant, which is 0. But when we get to C, C is changing. So we put what? Dash. Now, when we get to D, D is also held constant at 0. Okay. Now, we now compare 0 with C. Please, so long as we are still comparing 0 with the next group, the group is going to be the same. We are not changing our group. Okay. It is after we are done with this particular group 0 that we are moving to the next group that we are going to open a new group altogether. But here we are only comparing 0 with midterm 4. Okay. And midterm 4, we can see that A is held constant at 0, right? B is changing, okay, from 0 to 1. C is held constant at 0. D is also held constant at 0, right? So you can only identify one bit change, and that one bit change occurred at B when 0 changed to 1. So we can merge 0 and 4 as well. Okay. If we merge 0 to 4, we know A was held constant at 0, but B changed from 0 to 1. So wherever our change occurred, we put our dash. C, what happened to C? C was also the same, right? Which is 0. D was also the same, 0. Now we compare 0 to 8, which is our last member in this group. Okay. So when you compare 0 to 8, we can see that the first bit, which is A, is changing from 0 to 1, right? So we've identified our first change. If we're able to identify even one more change, we cannot merge. So B, 0 to 0, nothing is changing. C, 0 to 0, nothing is changing. D, 0 to 0, nothing is changing. So it means that the bit change is only 1, right? Which is at 0, 0 and 8. So we can merge the two. So now this becomes one group, okay? And our A was changing, so we put dash. Our B was constant, C was constant, D was also constant. So we've been able to work out everything for group 0. So now we can take our group 0. We can take minterm 0, right? So we are done with minterm 0. And then we are done with the entire group 0 also. We are not coming back to it again. We've been able to successfully run, merge it with the subsequent group. Now, we come and take 1 also, and then we repeat the same process. We said that we cannot compare two members of the same group. Okay, so you can only compare a member of the current group to a member of the next succeeding group. So that means that this is 1 belongs to group 1. The succeeding group is for group 2. So we run a comparison. So minterm 1 and then minterm 6. Let's compare. Our first bit is what? 0, right? So we have 0 here, we have 0 here. Second bit is 0. We have 0 here. This has changed to 1. So we've identified the first bit change. Let's go to the next. We have 0. This has changed to 1. We have identified our second bit change. Let's go to the third. We have 1, we have 0. Our third bit change. So how many bits are changing? 3 bits are changing. So can we merge it or not?
You can merge.
You cannot merge. Okay. Please, I forgot to close this group. Since we've already done comparing group 0 with group 1, it means this is one group. So we have to open one new group, which is group 2. Please, you all understand why we opened a new group, right? It's because we take group 0 as complete. So it means everything else that we do is a new group altogether, which is group 1. Okay. So now we know we cannot merge these two. Now let's see if we can merge 1 and then 2. Minterm 1 and minterm 9. If we check this, the first bit, A changes from 0 to 1, right? B remains constant. So if we identify one change, B remains constant at 0, 0. C remains constant at 0, 0. D remains constant at 1, 1, right? So you can see here is 1, here is 1. So it also remains constant. So it means only one bit is changing. And the bit that is changing at where? It's changing at A, right? Where A changed from 0 to 1. So it means you can merge group 1 and group 9. Please, did we all see that?
Yes, sir.
Or I should take it again?
Okay, one more.
One more, okay. So when we take group
Please,
1,
please, there's a hand up.
okay. So please, you can ask your question. Yes, Mr. Emmanuel.
Yes, please, your line was breaking.
Please come again.
Yeah, please, I said your line was breaking.
My line was breaking. Oh, okay, okay. Is it better now? Or is it still breaking?
Oh, I think your network is okay.
My network is okay. 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 So we said that we were comparing 1 and 9. We attempted to merge midterm 1 and midterm 6, but it was not successful because we had 3 different bits changing. Okay, so we could not merge 1 and 6. So we came to compare 1 and 9, right? And 1 and 9, when we compared, realize that 1 at our bit A, it was 0, 0 for both. Okay, bits, no, bit A, it was 0, 1 for the first and second, right? So we could see it was changing from 0 to 1. Bit B, it was 0, 0. We can see it was held constant at 0. Bit C, 0, 0, held constant at 0 again. Bit D, it's 1 and 1. So we can see 1 here, we can see 1 here. It's also been held constant at 1. Nothing is changing. So we can see that only one bit has changed so far, which is at A. Okay, so that means that we can merge it because it satisfies our rule that there should be only one bit change. And the bits changed at A, right, which is the first bit. So that place we put dash there. Now B was held constant at 0, 0, so we put 0. C was held constant at 0, 0, so we put 0. D was held constant at 1, 1, so we put 1. Are you okay now?
Yes, sir.
All right. So now you see what we did with 1. We can see that in that particular group here, we have 2 midterm, 2 midterm, 4 midterm, 8. We repeat the same comparison for all of them with the next group. Okay, so we are comparing group 1 to group 2. But you can see that group 1 alone has 4 members. We want to make sure that we compare all the members with the next group in the same manner. So we come and take midterm 2, and then we compare this one to this as well. Please, can we see that? So we are done comparing this, so we will take that right. So we come and compare the next one. So we have 0, 0, 1, 0, and then 0, 1, 1, 0. If we check A is 0, 0, it has passed. B is 0, 1, it has changed. So we have identified one change. C is 1, 1, it has passed, right? D is 0, 0, it has passed. Can we see that? Because that one was also held constant. So the only change that we can identify is at B, where 0 changed to 1. Apart from that, every other bit was held at the same value and was not changed. Please, have you been able to identify that?
Yes, sir.
All right. So if we are recording this, that is 2 and 9. No, 2 and 6, sorry. Please, it will really help if probably after this class, just take your question. Just take the question, even if you understand, take the question. That's if you don't already understand it already, okay, and you think you understand it, still take the question, and then ignore the solution and try repeating the entire process again. If you forget something, refer. That will just help it stick, okay? Else you sleep and wake up, and then since the process is plenty, it will not stick when you sleep and wake up. So just try repeating it yourself from memory, and that will make it stick, okay? So 2 and 6, we compare 2 and 6, right? And we said A was held constant as 0 and 0, so we put our 0 there. B changed from 0 to 1, so we put dash. C was held at 1, so 1, 1, we put our 1. D was held at 0, so we put our 0, that's constant, right? So now we can say that we've compared 2 and 6, right? Now we come and compare 2 and 9, okay? So we come and compare 2 and 9. When we compare 2 and 9, what do we have? 0 is changing to 1, first change. 0 and 0 constant. 1 is changing to 0, second change. So we know 2 and 9 is not possible, right? So we know 2 and 9 is not possible. What have I done? So we know 2 and 9 is not possible. So we take this and say we are done, because we cannot make 2 and 9, because at least 2 beside. Then we come to midterm 4, and repeat same process. We compare with this. And then when we are done comparing this, we compare with this. So let's compare midterm 4 and midterm 6 and see. Midterm 4 and midterm 6, 0, 0 at A, 1, 1 at B, 0, 1 at C. So C is changing from 0 to 1. And D is 0, 0, right? It is the same. So the change only occurred at C, which is only one big change. So we can record, right? So we say 0, 0 at, this is what, 4 and 6, okay. So 4 and 6, 0, 0 did not change. So we put as we retain our 0. 1 and 1 did not change, so we retain our 1. 0, 1 changed, so we put our dash. And then 0, 0 did not change, so we put our 0. Are you together? Then we come to our next one, which is 4 and 9. 4 and 9, 0 and 1, there is a change. 1 and 0, there is a change. We already identified two changes, so we can say that that will not work. Okay. So technically, we can say we are done with 4 as well. So we are going to repeat this. It's just the same thing, but we'll keep on repeating it till we've covered everything. Okay. So now we come and test for 8 also, or try to see if we can merge 8 also. So let's compare 8 and 6. 8 and 6, 0, 1, it has changed. 0, 1, 1, 0 has changed. 0, 1, 2 changes, it will not work. 0, 1 again, 3 changes, it will not work. So 8 and 6 will not work. Let's check 8 and 9. 1 and 1, constant. 0 and 0, constant. 0 and 0, constant. 0 and 1, only one big change. So it means 8 and 9 will work, right? So we have 8. Let me write it for. So we have 8, comma, then we have 9. Okay, and then 8 and 9, we said that 1 and 1 was constant, so we put 1. Then 0 and 0 constants, we keep our 0. We have 0, 0 constant, we keep our 0. 0, 1 is changing, we put our dash right there, right? Okay, so now we've fully compared all members in group 1 to group 2. So now we can say that we are done. So we just finished with 8, right? So we can see that all 4 members have now been compared successfully. So we are now done with group 1. So once we are done with group 1, you know we have to also close the group here, right? Please, are we all okay? I think let me pause and take questions. Okay. Please, anyone with a question before we proceed? Anyone with a question? Well, let's say you all understand, right? Okay. All right. So now we are done with the entire group 1. So we've closed our group. So now you can open a new group and we call that 2, right? So 2, let's see what we can do with 2. So 2, we have 2 members, which is minterm 6 and minterm 9, right? So we want to compare them with the next group. So let's identify the next group. The next group is group 3, right? So we will compare minterm 6, which is the first member, with 11 and 13. I think for this one, it will be faster because this one only has 2 members. Okay, so it will be much faster. So now let's compare 6 and 11. 6 and 11, you can see 0 is changing to 1, right? So we've identified the first change. 1 is changing to 0. Second change, so we don't have to even bother because we know it will not work. 2 bits are already changing. Let's compare 6 and 13. Okay, so 6 and 13, 0 is changing to 1, first change. 1 and 1, constant. 1 and 0, second change. It will not work. So it means for 6, we cannot even merge 6 with any other group or any other of the next group. So we know we are done with 6. Okay, so we can now take 6. Now let's take 9 and do the same thing for 9. So 9, we compare 9 to 11, then 9 to 13. So let's compare 9 to 11. We have 1, 1 constant, 0, 0 constant, 0, 1 first change, 1, 1 constant. So only 1 bit is changing, right? At C. So it qualifies. It means we can merge 9 and 11. 9, 11. And what are the merged values? We have 1, 1 is constant, so we bring our 1. 0, 0 constant, so bring our 0. 0, 1 is changing, so we put our dash. And then we have our 1, 1 constant, so we bring our 1. Okay. And then we have what? We have 9 and 13. Let's compare 9 and 13. So 9 and 13, we have 1, 1 at A. We have 0, 1 at B. B is changing, right? C, we have 0, 0 at C. We have 1, 1 at D. So apart from B, nothing else is changing. So only 1 bit change. That qualifies. So it means we can merge 9 and 13 as well. So 9, 13. So 9, 13. What does 9, 13 give us? We have 1, 1. So we put our 1 at A. B, 0, 1 is changing. So we put our dash. 0, 0 constant. So we put our 0. And at our D, we have what? 1, 1. So we put our 1, right? So now we've been able to complete our group 2, right? We've compared everything in our group 2. That is, this is done, right? So since this is done, now we can now do comparison for our last group. So we open a new group, right? Which we can call group 3. Because we are done with everything from group 2 in the previous table. And this will be our last comparison that we run. And then our table is complete. So Let's compare 11 to 15. This one is even much more simple and direct. Okay. So this will give us group 3, right? So 11 to 15, we have at A, we have 1, 1, right? So 1, 1 is the same. We have 0, 1. 0, 1 is changing, right? So we've identified our first change. 1, 1 is the same. 1, 1 is the same. So only B changed to 0, 1, right? So it means our A at 11 and 15, our A was held constant at 1. Our B changed from 0 to 1, so we put dash. Our C held constant at 1, so we put 1. D held constant at 1, so we put 1. Then we come and compare. Now we are done with our 11, right? So let's take our 11 to indicate we are done working with it. And now let's come to our 13, which is our last one. So we compare 13 with 15. So 13, we have 1, 1 the same, 1, 1 the same, 0, 1 changing, 1, 1 the same. So we can see that only our C change, right? So we have our 13 and 15. At our A was held constant at 1. Our B held constant at 1. C changed, so we put dash. And then our D was held constant at 1. Okay. So now we can say that we are done working with this particular. Please, sorry for the mistake. I think writing on the screen with this writing tool is a little bit difficult. So it's just difficult to write. So now, since we are done with this table, we are done with this right here. So automatically we've completed this working with this table. So now we can now move to this table. So we repeat the same process for this table. Okay. And I believe this is going to be our last. The reason why I'm saying this is going to be our last is that basically everything is 4 variables. So if the minimized form, I believe, should result in 3 variables. So let's say 4, but I believe this should be our last. So we have our group. We are going to do the same thing. This thing becoming difficult. So we have our group again. Okay. We have our merged pair. We could just write it as MP. Okay. We have our A. We have our B. We have our C. We have our D. All right. So we now have our paired table present. Okay. So we are going to repeat what we did. We are just going to compare again and look out for 1 bit change. And when we identify that 1 bit change, we put a dash at where the bit changed. Okay. Please, are we together? Are we pleased together?
Please come. Please go again.
Okay. So, all right. So this table is going to be the same as what we did previously. We are going to compare in the same manner, in the same fashion. Okay. We are just going to compare group 0 to group 1, group 1 to group 2, group 2 to group 3. And we are looking out for only 1 bit change and nothing more. So if there is only 1 bit change in two comparisons, then we merge. If there isn't, we cannot merge. Okay. So the trick here is that once you get here anyhow, you see that now automatically you've done your first comparison. So some bits are already dash, dash, dash. That means that it becomes very, very difficult for you to be able to merge. So usually the number of members you get from this, or the number of merge pairs you can derive from this, will be very, 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 very limited. Okay. I don't know if you are getting me. You've already looked for the first batch of changes. So now trying to look for the second big change will be very difficult to find, which means that let's just move straight forward. So you start with comparing now. This pair is 0, 1, right? 0 and 1. So you compare this to this, right? First. Now 0 and 1, we are comparing it to 1 and what? Is it 1 and 7 or 1 and 9?
I think it's 1 and
I think
9.
1 and 9 is 1 and 9. Yeah, 1 and 9, because in the given mean terms, there is no 7 there. Okay, so if you compare this, we have 0 is changing to dash, first change. 0 to 0, good. 0 to 0, good. Dash is changing to 1, second change. That is not possible. So we cannot merge because we've identified two changes. Then you come and compare this to this. 0, 0, good. 0 to dash, first change. 0 to 1, second change. So immediately you identify a second change. There is no need even checking for a third change because it's not necessary. So let's look at our next comparison. We have 0 and 0, good. 0, 1, first change. 0 dash, another change. So we have two changes already, so no need to continue. So we come to 0 and the last one, right? So 0, 1, and then 8, 9. So we have 0, 1, we've identified first change. Then 0, 0, good. 0, 0, good. Dash, dash, good. So please, have you identified it? We've now seen that at 0 and 1, comparing that to 8 and 9, the only bit that change was at A. We've identified our one bit change, which matches the rule. So we can now open our group 1. And group 1, the first member will be 1, 0. So we merge 0, 1 is merging with what? 8 and 9, right? Eight and 9. And A was changing from 0 to 1, so we put dash. B was held constant at 0, so we put at 0. C was held constant at 0, so we put at 0. And D is dash dash, so we just put our dash there. Okay, or you can just ignore dash, you let's just maintain it as dash. Okay, so now we are done with our 0 here. So we take 0, 1. So we come and do the same thing for 0, 2. Let's compare 0, 2. So now we compare 0, 2 to 1, 7. We have 0 dash, first change, 0, 0, good, dash 0. It will not work. So we come and compare it to this one. We have 0, 0, good, 0 dash, first change, 0 dash 1, second change. It will not work. Then let's compare our third one. We have 0, 0, good, 0, 1, first change, dash, dash, good. Then we have 0, 0. So we can see that only one change has occurred. A is 0, 0. B is 0, 1. That is where our change occurs. C is dash, dash, the same. D is 0, 0, the same. So you can see that 0, 2, and 4, 6. We can merge them. Okay, so we have 0, 2, let me represent this for 0, 2, I'm sorry. So 0, 2, 4, then we have 6. So this is our new group, right? And we said at our new group, A was held constant at what? At 0, right? B was held, let me see, B changed from 0 to 1, so dash. We can see that here. B was 0, here B was 1, first change. C was dash dash. So we put our dash. D is 0, 0. So we put am I right? Yeah, D. No, D. Yeah, 0, 0, 0, 0. So that's 0. That's 0. All right, so I believe we are all cool so far. I believe we are all cool so far. All right, so let's continue. Are we all okay so far?
Yes, please.
All right, so now that we are done with this, we come in, it's just repeating the same thing. So we come and repeat the same thing for the next one. We compare with this. So if we compare with this, we compare with that, we compare with this, and then we compare with that. So when you compare with this, let's do that very fast. 0 dash is changing, dash 0 is changing. We've already identified 2 changes. 0, 0 constant good, dash dash constant good. 0, 1 is changing. 0, 0, 0, 0, 1 is changing. Let me see. We have 0, 4, 2, 6, right?
The last one is changing. The D is changing.
The D is changing. Let me check the corresponding D value. The D is changing.
We are checking for 19, right?
Yeah, I'm coming.
08 and 19.
Okay, we are checking for 08 and 19. Okay, I
Yes,
think
yes,
I was just confusing. Oh,
It's
08, 08. Are you checking 04 or 08?
Is there? I see a comparing 04 right now.
04, yeah, 04, 04.
Okay, so 04. It will change at A.
Yeah, so 04. A
It will
is
change at
1.
A and D. A and D. So it's not. It's not part.
Oh, okay, so this was 1. So
Yes.
did I write 1 like this? Okay, so A is changing, B is changing, right? So 2 changes we ignore. Then if we come to the last one, we have A 01 is changing, dash 0 is changing. So that means that we cannot merge with anything. We cannot work out any merger here. Okay, so if you take 08, we repeat the same thing. So let's see. We have dash 0, 0, 0, 0. Yeah, so we can have a measure here, right? Let me see, dash 0, 0, 0, 0, 0, 1. Yeah.
Is it 04 or 08?
Come again.
Are we using the 04
No,
or 08?
we are comparing 08 and 19.
19. Okay.
Yeah. So let me see. We have dash. We put. Oh, here I didn't even write the full minterms. What and what do you even compare here? Yeah, 0246. Okay, so we are comparing 08 to 19, right? So dash 0, 0, dash 00001. Yeah, only one bit change. So we have 0849. So what's happening to this thing? I think this was dash. This was, I believe, 0. Dash, right? Yeah. So let's continue. So we have 0408. We have 1919, not 49. 19, right? So that gave the corresponding A values are dash dash. So we have dash dash. Then 00, 0. Then we have 00, 0, and then 01. We have dash. Okay, let me clarify this. You see, now we've had a scenario here where this one here, you can see this is the same as this, right? Which is dash 00 dash. We have dash 00 dash. So you cannot repeat. Okay, so you let's continue. When you're done, I would clarify that. But please, if you have something like this, one has to cancel out, or you cannot repeat the same expression for the prime implicant. Okay, it's like performing the same prime implicant twice or two times. You cannot. It cannot happen. Okay, that is considered redundant. So you just cross it out. But let's continue. So now we are done with the fourth one, right? So we are now done with this entire group. Now we'll come and look at this group, right? So let's cross this out. And now we can look at group 2. So group 2, please, let's just cancel this out straight away, okay, so that it doesn't confuse us. So please, do you understand why I'm canceling it out?
No.
Please, do you understand why I'm canceling it out?
No, sir. Please go over here.
All right, so I was saying that if we were able to merge 08 and 19, right? But when you merge 0819, when we trace the A, B, C, D, we have dash 00 dash. But you can already see that if you check 0189, that particular prime implicant is already covered. I don't know if you are getting me. So we cannot cover the same prime implicant twice. It creates a redundant value. Okay, so let's look at it. Dash 00 dash. The actual prime implicant for that is B prime, D prime, right? Can we see that? So we can trace, we have B being 0. So we have B prime, C, no, not B prime, B prime, B prime, C prime. Okay, we have B being 0. Then we have C also being 0. So B prime, C prime. Please, can we all see that? So we have B prime, C prime. If you come and look at this particular place, which is 0819, also dash 00 dash, if you trace 0 to B, you can see that that gives us another B prime again. C to 0, that gives us another C prime again. Please, so have you seen what is happening? So we have a case where the same prime implicant has been covered already. So if we repeat those two in one expression, it creates a redundant value, which is but offers basically no value to what we are doing. Okay, so we just cancel one out. It is not allowed, or it is not permissible to do this or to repeat. Let's say one expression. You have A, B, and then another AB repeated in that same expression, you know. Okay, one is you can consider one of it as redundant. So please, that's why I cancel that. So please, we get that now. So please, do you get the reason why I cancelled 0819 out? Hello.
Yes, sir.
All right. So please, when you are working, anytime you encounter the same scenario, the same rule applies. Okay, but the reason why I was saying that let's finish first is that we want to be sure that we cannot minimize any further before we do our cancellation or our crossing out. But regardless, it has not changed our final value. That's why I still was like, let's cancel that anyways. So we now come to group one, okay, and then we run the same comparison. So we compare this to this to that. Let's run the comparison for group two. All right, so let's run the comparison for group two. So we have -1, first change, 0, 0, no change, 0 dash, second change. So that means that wouldn't work. Let's compare 1, 9 to 9, 13. We have -1, first change, 0, 1, second change. So that wouldn't work. Okay. We cannot match. So we take this, then we do the same thing. So we have a 0, 1, first change, -0, second change. So it will not work. The next one, 0, 1, first change, dash, okay, 1, 0, another change. It will not work. So we've identified two changes already, so that will not work. So this is also a pass. We skip that. So let's come to this. We are comparing this to that. So we have 1, 1, we have 1, 0, first change, dash, good, 0, 1, second change. It will not work. So now you compare 4, 6 to 9, 13. What do we have? 1, 1, 1 dash, first change, -0, second change. So it will not work either. So we are done working with that. And now let's do our comparison for 8, 9, 9, 11, and then 8, 9, 9, 13. And let's see if it's something work out. So we have 1, 1, good, 0, 0, good, 0 dash, first change, -1, second change. It will not work. Then we have the next one. We have 1, 1, good, 0 dash. It will not first change. We have 0, 0, good, -1. We have second change. Okay, so that will not work as well. So we are done with this particular thing here. So since group 2 has not been used, we can just use, oh no, let's label this group 0 instead. And let's label this group 1. Okay. So since group 1 has not been used, we can just use that for the next comparison. So let's compare 9, 11, and then 11, 15, and then 9, 11, and then 13, 15. And let's see if we can do something with this. So 9, 11, and 11, 15, we have 1, 1, good, 0 dash, first change, -1, second change. So that will not work. Then 9, 11, 13, 15, we have 1, 1, good, 0, 1, first change, dash, good, 1, 1, good. So this will work. So you can see that the only bit is changing as B, right? 1, 1 is constant. 0, 1 changed. Dash, constant. 1, 1 not changed. Or was held constant. So only B changed. So it means 9, 11, 13, 15 will work. So we have 9, we have 11, comma, we have 13, comma, and then we have 15. Their corresponding A value is what's it? 9. Their A value is 1, right? So 1, 1. B is 0, 1, so we put dash. C is dash, dash, we put dash. D is 1, 1, so we put 1. So now let's do our final comparison and then we are done with this. So our final comparison will be here, right? All right, so here we have 9, 13, and 11, 15. Let me see. So 9, 13, 11, 15. We have 1, 1, good, dash, dash, good, 0, 1, changing, 1, 1, good. So that will merge. Okay. So let's merge that. We have 9, 11, 9, 13 rather, right? Let me see. Yeah, 9, 13. Comma. Then we have 11, 15. Okay. So A was held at 1, B was a dash, right? C changed from 0 to 1, so we put dash. D was held at 1, so we put 1. Okay, so that's it. Oh no, so please, can you all see what is happening here again? Please, can everybody look at the table? You can see that 9, 11, 13, 15, and 9, 13, 11, and 15, they are having the same values again. That is 1 dash dash 1. But that prime implicant has already been covered by this. So repeating this will create a redundant value. So we cancel it again. Okay. So we have 9, 13, 13, 15. Let's see. Comparing 1 and 1, dash and 1 will not work. 0 dash will not work. So I think we are done with that. So let's take that. And then we are done. Okay. So please, can we all see what we've had so far? If anybody has any questions at this point, you can ask. Any question pertaining to why anything was cancelled or any sad thing, please. Any questions so far before we progress? Any questions?
So please, Emmanuel has a hand on.
Is you're okay with everything?
Emmanuel's hand is up.
All right, please, you can ask your question.
Yes, so please, I wanted to ask. So for the cancellation, should it be like, is it compulsory for us to?
Oh. Please, can you...
Yeah, Loza, can you hear me, sir?
Yes, please, I can hear you.
Yes, so please, I was asking for the cancellation of the identical minterms. Must it be the second one? Is it always compulsory to always cancel the second one?
Yeah. If it is covered in the first, immediately there is a repeat. It has already been covered. So the second one needs to be cancelled. Okay. So there is no need repeating the same expression again or the same prime implicant whilst the prime implicant has already been covered, or those same set of prime implicants has already been covered by another. Okay. So automatically the resulting expression is considered wrong or not in its minimized form. Let's just take those off. So please, are we all together? Are we all together? Are we all together?
Yes, I have together.
All right. So if we are, I think this is the one of the most important parts. So if we've all gotten it up to this point, then I can say that we are good. Okay. So here, if you compare further, you realize nothing can be done, right? If you compare this to this, dash, like this is changing, this is changing, this is changing, this is changing. Compare this to this, you still have the same thing happening. This is changing, this is changing. There's just nothing you can do from here. So you've just merged to the last point. You can't merge anything here again. Okay, so as at this point, you can consider this as complete. I mean, please, are we all okay? All right. So if we are all okay, then let's now denote. Please, if you don't get it, yeah, Mr. Emmanuel.
Yeah, Jose, please, I wanted to ask for the last time. So if there are three identical minterms, so we're going to cancel the last two.
So if you have three identical prime implicants, right? Yes,
Yeah,
you
I'm
can
able
repeat the three.
to like also.
Yes, you can only repeat the first. That the other two has to be taken out. You cannot repeat them. You create redundancies. You cannot repeat them. Okay, you cannot repeat them. Is do you get it now? All right. So from here, we have to now look at our prime implicants or try to deduce our prime implicants from this. Okay, or from what we've done so far. Okay, so let's deduce our prime implicants. So we were left with, from group 1, we were left with 0189, right? And 0189, everything was dash dash except at B and C, right? Please, can we all see that?
Yes, sir.
Exactly. Everything was dash dash except at B and C, and that's what we are interested in. So B has a value, C has a value. Okay. So we know that what was left was B and C. But then B is 0, not 1. If B was 1, we would have left it like that. If C was 1, we would have also left it like that. But if it is 0, you take the prime of that variable. Okay. So you know the prime of 1 is 0. So this is B prime, C prime. Can you see that? Let me denote it differently. So we have B prime, and then you have C prime. Please, do you all see how we had a B prime, C prime?
Yes, sir.
All right, then you go to the next. You have A left, A is 0, right? So do you write A or you write A prime? Hello, please, do you write 0, A or write A prime?
Please, which one? We write A prime.
Yeah, A is 0, right? You can see here the second set of mean terms. We have
Yes.
0, right?
Yes, sir.
At A. So A
So A
prime.
prime.
So A prime. And then at D, right? D is also 0. So we also bring D prime, right?
Prime. Yeah.
So we have B prime, C prime, A prime, D prime. And then here we have 1, 1 at A and D, right? Everything else is dashed. So we bring our AD. We don't need to bring our prime, right? There is no need to bring our prime because it is not 0, it is 1. If it is 1, we don't bring our prime, okay? So you can see that our set of prime implicants. So please, what we obtain here is our set of prime implicants. Our set of prime implicants is B prime, C prime, and then we also had or someone can decide to write it as plus, okay? But let me just write it as A prime, B prime, and we also obtained A D. Okay, so now we are done with the first major requirement of the question or of the problem. We've been able to figure out, I think we had the same thing in our assignment, almost the same thing, a variation of this question in our assignments, right? So we have Pi is equal to B prime, C prime, we have A prime. If your microphone is on, can mute it for us, okay? Then we have A, D. All right. So now we want to find our essential prime implicants. And please, to find our essential prime implicants, we are going to draw another table again, okay? And this one, let's look at this a little steadily, okay? Okay. We draw our table in this manner. You see, in the question gave a group of mean terms, right? What was the mean terms that was given in the question? Where is this thing? Exactly, we have 0, 1, 2, 4, 6, 8, 9, 11, 13, 15. 0, 1, 2, 4. Let me write that. So we have 0, 1, 2, 4. We have what again?
2, 4, 6, 8, 9.
Okay, 6, 8, 9, 11, 13,
11,
15.
13, 15.
All right. Six, 8, 9, 11, 13, 15. Okay. All right, so this Sorry. These are all our mean terms, right? But then we had our prime implicants being B prime, C prime, right? So B prime, C prime. And please, which mean terms did B prime, C prime cover? Let's go back and check the grouping from the table here. All right. So you can see that B prime, C prime, it's covered this particular set of mean terms, which is 0, 1, 8, 9, right? So come down and write it there. So, oh goodness. So 0, 1, 8, 9. So we write it here. 0, 1, 8, 9. Okay, so 8, 9. All right. And then you see, you come and do your asterisk here. So where 0 is here, you put asterisk 1, you put it here. 8, you put asterisk 9, you put asterisk, okay? And then the second one, you have A prime, D prime. So you have A prime, D prime. So A prime, D prime, it's covered which mean terms, which is 0, 2, 4, and 6, right? So you put asterisk at 0, 2, 4, and then 6. Okay. Then you come again. The third one is what? A prime D, right? So you have A prime D, that covered what? 9, 11, 13, and 15. So you come and do your asterisk at 9, 11, 13, and 15. Okay. So after that, you come and now inspect. There should be lines here, which will make you see that clearly. Okay. Let me put the lines there. Let me see. This is here, right? 9, 11. Okay. So please, what you are going to do is that circle your asterisks that are standing alone, like this one, like this one. You see, there are, if some of them, if you check the line here, like mean term 0, you can see 2 asterisks. If the asterisks are double there, don't circle. Circle the ones that are only standing alone. So here is standing alone, or it's only covered by 4. Here is standing alone. 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 Okay. So when you are done, you can see these ones are circled, right? Trace it to the corresponding mean terms. The corresponding mean terms is what? B prime, C prime. These ones two are standing alone. They are not covered by any other prime implicants. Trace it. Yes, sir.
Okay.
You got anything?
Yeah. Yes, sir.
All right. So if you trace it, you get A prime, D prime. And then here, these 3 are also standing alone. So if you trace it to the corresponding D prime, prime implicants, you get AD. Yes, sir.
Please, the numbers where the 9 is located.
Yeah.
The column is having X is there.
Oh, okay. X is 2. X is 2. Good.
Yes.
Thanks for the observation. That means you cannot circle that. Okay.
Yes, sir.
You cannot circle that. Regardless, we can see that this two have not been covered. Okay, so that means we can work with them. Okay, but there are some instances that you realize that for a particular set of prime implicants like A prime, D prime, automatically other prime implicants has covered them. You see, the two that we cancelled, if you left them there and we came here, you realize that they've all been covered already. So they would have been eliminated regardless, but it would just make the process overly tedious. So now the resulting expression that you get here will be your simplified or your minimized Boolean expression, okay? And the individual product terms in here are your essential prime implicants. But then the entire expression together is your minimized expression. So we've now applied the QUINE McCLUSKEY minimization method to completely minimize the given function and its corresponding minterms. Okay. Are you all okay?
We are fine, sir.
Okay. Okay. So I think time is fast spent. So I'll leave you a question. Okay. Try this question on your own. All right. So this one, the variables are more. Okay. So just try. So you have a function, and a function is given with variables a, comma, b, comma, c, comma, d, comma, e, comma, f, comma, g. Okay. And
Yeah,
a
we are doing it.
corresponding, yeah. Please, this is what QUINE McCLUSKEY minimization method is meant for. Okay, so the other one is just to understand or to help you understand. So the mean terms are, but even this one is much more simpler technically. So we have 20, 28, 52, and then 16. So using the QUINE McCLUSKEY minimization method, simplify the function for the given expression. Okay, I mean simplify the given function. Okay, so I believe we are okay. So please, when solving this, the first method is to find the binary equivalence of 20, 28, 52, and 60. And after you found the binary equivalence of them, fill the rest of the zeros so that all the variables are one way or the other filled. Okay. After you ensure that the variables are filled and you rightly obtain the binary equivalence of everything, you can now group them, okay, according to the number of ones present. So all the mean terms with 1 ones take one group, 2 ones take another group, 3 ones take another group, 4 will take another group, etc. Then after that, then you group your pairs. Okay. So you are going to find your merged pairs, or you merge your pairs. And after you've merged your pairs, you can now proceed to find a prime implicant and then the essential prime implicants. And then you are good. Okay. So I think one person, anyone who is able to complete this solution can take a picture and send it to the platform so that it guides the others to also do this. All right, so thank you very much for being here tonight. I think we close very late. So we will meet again in our next session. So I think in our next session, we can now start looking at combinational logic, right? Yeah. So we can look at that and then move from there. All right, then have a very wonderful day.